So, welcome everybody. It's my great pleasure to have our next speaker in the seminar, which is Andrew Sageman-Furnas, and we will talk about navigating the space of Chebyshev nets.
Hi, thank you, and thanks for the opportunity to talk to you all today. Please, at the very beginning, let me say, if you have a question at any time, feel free to interrupt. Especially in this sitting, I can feel like I'm just talking to myself sometimes. So definitely interrupt or type into the chat window, and I will be able to see it, or someone else will call out. So yeah, let me start by showing with these three pictures here that you see. And I just want to tell you a little bit about my work. So unlike everything else that you may see in the world, where we sort of definitely know to understand it as more of a smooth structure or as a discrete structure, my work tries to focus on what I call the intermediary or the mesoscale. So here, for example, we see a picture of two cells, and that cell is actually built of a couple of different types of networks. The network that we see in purple or blue, that may be thought of as sort of somehow a background medium. And then you also have a network in yellow, which is more obviously discrete. And so if you want to model these filament networks inside cells, the question is, do you use a discrete model or do you use some sort of smooth model or continuum model? In contrast to that, there are also mesoscale structures that have a structured intermediary scale. This may be down at the very small. For example, when you put a stent inside of an artery or a vein, then you can see there that you have this structure, this grid type of structure in the object that you place inside of the artery. Going to the very large scale, you also see here on the right an architectural grid shell, where when you squint, you see this beautiful smooth structure, but actually it's built of discrete pieces. And so the question is, do we understand this as a discrete object or as a smooth object? And actually having a structured mesoscale can allow for different types of deformations that may not be allowed with objects that are smooth all the way through. So here, for example, is one of the wheels on a practice Mars rover. And these wheels are a woven metal structure or flexible mesh, which actually allows them to take on the different shapes where they may need to go when it rolls over the ground of Mars. And so what I want to understand in sort of a large scale, one of my main research questions is to explore and understand this sort of constrained shape space. I like to call this the stretch spectrum. So on the left, what we can see here is a piece of paper, and that's put over a sphere. And as soon as you start to go down the sphere, you see that you get these wrinkles that start to occur. Next, you have sort of a paper towel, and then a dress shirt or some jeans and t-shirt. And all the way to the right, you can imagine that you pull like a swim cap tight, and it just clings to your head with no wrinkles or ruffles at all. And so what you can see here is that on the left, we have something that is sort of has no stretch at all and cannot encode curvature. On the right, we have something which stretches the same in all directions and can encode curvature very well. And in between, we have objects that have different mesostructures, and the type of that mesostructure allows us to encode some curvature or varying degrees of curvature. And so in this talk, I want to focus on a particular intermediary mesostructure, which is grids of inextensible rods. So this I want to take as a geometric principle. So that means we could be talking about a piece of woven fabric. For example, this skirt you see on the left. It could also be a piece of wire mesh, like the strainer in your kitchen, or it could be a large sort of elastic grid shell built out of only tens of rods, as opposed to the thousands of rods from the woven fabric. But the important thing here is the inextensibility of these rods in two directions. And what we want to do is use techniques from differential geometry and its discrete analogs to try and model these shapes. So the model that we're going to build from was introduced by Pafnuty Chebyshev in 1878. You probably are more familiar with his work maybe in probability theory or many of the other things that he did, but he also studied fabric. And the story goes that he was actually hired by the Russian army to try to minimize the amount of fabric required to make the military uniforms. And so he said, okay, how do I actually understand what shapes a piece of fabric can make? And so we have these two directions where along the yarns, and these are not allowed to extend. But the way that you actually get a billowing form from the skirt is by the shearing of those rods. So the rods cannot extend, but they're able to shear with respect to each other and change their infinitesimal area element. Here is just to really drive this point home, because the entire talk will be about Chebyshev nets. On the left, we have this inextensibility along two directions, but this piece of wire mesh is still allowed to shear. Are the videos coming through okay? Can someone tell me if the videos are coming through okay? Okay, great, thank you. So what we're going to see today is we're going to start with just the differential geometry of a Chebyshev net. Then we'll move into an application to elastic grid shells, try to understand the challenges that arise from these types of systems, and then go into ways to overcome these challenges that have to do with the rise of singularities in the underlying partial differential equation. So what is a Chebyshev net? A Chebyshev net on a given surface is a mapping, or actually a specific set of coordinates on this surface from the plane to the surface, such that the magnitude of the partial derivatives is 1. So it has unit length tangent vectors. This physically corresponds to the inextensibility of the u and the v directions, but those two are still allowed to shear with respect to each other. So this is sort of a differential geometric model of a piece of woven fabric. You use the parametrization to encode the geometry of the inextensibility condition. And so the entire shape, or the ability to actually cover this surface in more than just a little bit of a local patch, is governed by the ability of this parametrization to shear across the surface. And when you write down the Gauss equation for this compatibility condition, you actually see that it links the angle between the two tangent vectors at every point, which I denote here by omega, and the Gaussian curvature of the surface. So in this surface, for example, a point may have negative Gaussian curvature because they bend in two different directions of space, whereas the exact same net, if you pass something with positive Gaussian curvature into it, then you can see that the tangent lines at the points change their shape to encode the underlying curvature. So it's a very important thing to understand that for a Chebyshev net, the domain with which you actually take your mapping can have a very important impact on the shapes that you can place this Chebyshev net on. So for example, if I take just a rectangular patch, then the boundary of that rectangular patch, if it's aligned with the inextensibility directions, then I don't have very much freedom because my boundary is itself inextensible. However, if I make a cut that is not axis aligned in the boundary, then I can imagine the collapse or the shearing between those infinitesimal tangent vectors, which allows me to encode things like the hyperbolic surface we see on the right, as well as the cylinder that we may get from an axis aligned domain. So Chebyshev himself actually said, we want to understand a shoulder. He said, okay, the best approximation to a shoulder is a hemisphere. Let's try to understand if we can put a Chebyshev net on a hemisphere. And so he wrote down and was able to actually solve the Gauss equation on the hemisphere. And what you see is that along the two axes of, sorry, can you see my mouse? I'm not sure if you can see my mouse. Yes, okay. So along the two axes here, these are inextensible, and so they have to map perfectly to 1/2 of the circumference of the sphere, right? On the other hand, in the diagonal direction, what you see is that because of the shearing that takes place from the underlying curvature, you can actually gain extension in that direction. So you don't have to start with a circular domain if the material were completely isotropic. So here, the fact that you have inextensibility just in these two directions and the ability to extend in the other directions means that you get shearing at these portions of the net, which give you that extra extension. Compare this region here, where you see shearing, versus here, where the inextensibility condition comes into play. So let's talk about our first application. This work was done with my collaborators in mechanical engineering, originally at MIT, and then they moved to EPFL. I worked closely with Cheng-Yeb Bak, who was a PhD student on this in the lab of Pedro Rice. So the idea was they came to me with with an exciting system that they wanted to study at the desktop scale. And they said, okay, let's study an elastic grid shell. So what is that? It is initially a planar object, which is built from one-dimensional rods. Each of these one-dimensional rods is a Euler elastica, so it tries to minimize its bending energy and is completely purely elastic. So if I bend it, then it immediately bounces back to being straight again, unless there is some resistance to hold it in place. So then this grid is actually made by laying it out parallel and perpendicular. And then there's a little bit of silicone or a little bit of material used to fuse the points so that the whole thing behaves like a mesh structure as opposed to just individual rods. And what you do to actuate this system is you take the circumference and you move those black points here onto a curve of smaller radius. So this we'll call the footprint boundary and the actuated boundary. So due to the inextensibility of these rods, each of which is still a smooth rod, you get a popping out into the plane. So in this particular example, you take a circular piece, you shrink it to a circular piece of smaller radius, and what is the shape that you get? So it immediately sort of buckles into something that has regions of positive curvature and regions of negative curvature, and looks sort of nothing like a sphere or something that at least they or I was able to predict in advance. And so they came to me and said, okay, these shapes are beautiful, but is it possible to actually design a target shape, right? I want to make not this shape, but a specific shape that I have in mind. So we went back to the drawing board and we said, okay, we have a beautiful way to do the forward design of buckled elastic grid shells, right? We have a simulation based on every rod, and using that, we can actuate the boundary and understand the shape as long as we minimize this bending energy subject to the inextensibility constraint. And at that point, because I had thought a little bit about Chebyshev nets, it started to come to my mind and said, okay, well, maybe we're getting higher order buckling because of a mismatch in the inextensibility constraint of each of the individual rods. So what would happen if we just used a Chebyshev net model to mitigate a length mismatch? And so we only use this inextensibility constraint and hope that the physical energy of bending can be a regularizer inside of the feasible space. So as a test case, what we did was I said, okay, there's sort of this Chebyshev net that's known on the hemisphere. Let's see if we can actually design a hemispherical elastic grid shell just by doing the most naive thing possible, which I couldn't believe could actually work. So the idea is we know that we have a map, the smooth map from Chebyshev himself, which goes from this planar region all the way onto the hemisphere. And so to get an elastic grid shell, we're going to take a guess or make an ansatz. And we're first going to do that by forming some grid with a finite number of rods, intersect the smooth domain with that grid, and record where the location of each of those points is along the boundary. Then we can look at the image of those points under the Chebyshev map. So they then are identified with a place along the circumference, or along the equator of the hemisphere. And we use those as the footprint boundary points and the actuated boundary points. And remember here that this guess does not use any bending at all, right? This is purely a geometric model. The existence of a Chebyshev net, these special coordinates from the plane onto the hemisphere. And surprisingly, it actually made the shape of a hemisphere, which I was really, really excited about, right? I mean, the deviation from being a perfect hemisphere was only about 2%, even though we had completely ignored this bending energy in the ansatz that we made. And actually, it turned out that we were able to go much further than this, but you can sort of piece together more complicated shapes using this Chebyshev net ansatz, both in the domain and on the surface that you want to target. So here, for example, we fused together a Chebyshev net on a portion of the hemisphere and a portion of the saddle to make this sort of mixed curvature shape that you see. And the entire thing here is done just by this geometric ansatz and worrying about and not worrying at all about the bending energy and hoping that it will sort of guide us to the correct solution, which it seems to do. So this is nice. We've now sort of taken this elastic grid shell problem and we started to reduce it down to thinking about a Chebyshev net. And so the next obvious question is, how big is the space of Chebyshev nets itself? Well, unfortunately, it turns out that actually the only provable known examples with large Gaussian curvature are surfaces of revolution and the hemisphere. So other than that, it is not known that there exists sort of singularity-free Chebyshev nets on very curved surfaces. It's known that on around every point on a surface, you can have a little patch of a Chebyshev net, and it's known that if there's not very much curvature at all, then you can have a Chebyshev net. But other than those two examples, we sort of have already exhausted everything that's known at that time. And so the question is, okay, well, what's actually going on here? Why is this problem so hard? And is it possible to find more interesting shapes that have more Gaussian curvature? And this is sort of the next piece that I want to talk about. So recall that if you want to put a Chebyshev net onto a given surface, then the compatibility condition or the Gauss equation for this to occur intrinsically is to have a relationship between the amount of shear in the Chebyshev net and the Gaussian curvature function of the surface. So for a fixed surface, the Gaussian curvature function is known, and we want to solve then this nonlinear hyperbolic differential equation along the target surface. The problem is that, as is well known, hyperbolic equations, when you propagate them out from some initial data, singularities are basically inevitable. They're not known where to occur, and they're sort of global obstructions by integrating along characteristics that prevent you from having very large solutions. So here, for example, let's go back to Chebyshev solution on a hemisphere. And let's try to actually extend this solution into the lower part, into the southern hemisphere. Well, what you see is that the shearing continues more and more and more and more until you get a collapse of this part of a hyperbola here in the domain collapses to a single point, which corresponds to a singularity on the surface because we have a line collapsing to a point. And this also could not be physically constructed. And how are we supposed to know that this singularity was going to occur there and not some other location on the sphere, right? So what are also these global obstructions that are known? What can we say by integrating along the characteristics? Well, when you integrate along the characteristics, that means you're actually integrating along the u and v, this hyperbolic differential equation. And it turns out that what you get on the right-hand side is something like an integrated Gaussian curvature, so a total Gaussian curvature. And on the left-hand side, you get something that has to do with interior angles of the net. And so you arrive at a result which was known to Hatzidakis just 1 year after Chebyshev came up with these nets, which is that every axis-aligned rectangular domain has a maximum amount of curvature that it can encode. And across any particular domain, you have many of these sub-rectangles, each of which can have at most 2 pi Gaussian curvature. So let's go back to the sphere example again. What you see is that the domain that corresponds to the hemisphere actually is very, very nice in cutting away portions of a larger rectangle here, shown in big red, which would include these singular points. So what we're seeing here, once again, is that the shape of the domain can have a really big impact on the curvature of the surface that you're allowed to encode. And if you accidentally include a little bit too much material in one place, then you may be running into a singularity later. And so what it comes down to is trying to solve this nonlinear hyperbolic differential equation and figuring out what the shape of the domain might be to make a more complicated surface, or to cover a more complicated surface than just the surface of revolution or a hemisphere, right? To some extent, you can think of what a tailor does when they try to build our clothes, and we know that our clothes have seams in it, or locations where you probably would run into a singularity if you didn't cut and then attach to a new piece of fabric, which isn't bound to the same compatibility condition, right? You have something which the compatibility condition is not satisfied across these seams. And so the idea is, okay, it's very challenging to know from an analytic perspective that I can go sort of 3 epsilon in this, epsilon in that direction, but only 2 epsilon in this other direction. And so therefore, the goal and sort of the idea is instead to navigate this space through computational design and fabrication, really with applications in mind. So I'm going to talk about, for the remaining time, 2 recent collaborations in computational fabrication, and they have 2 different flavors. The first is sort of, what can you build with a single piece of material? So the single patch Chebyshev net, and how far can we push it? How much more than 2 pi Gaussian curvature can we get, and what sort of complicated shapes can we make? And then the second thing that I'll talk about here is a very recent project from end of 2019, where we tried to understand, okay, we know that in reality, you probably have to have singularities. Is it possible to actually allow only certain types of singularities and therefore still make something fabricatable? And that required a whole reformulation of the problem. So what we'll see here is, in this sort of design of singularity-free Chebyshev nets, we're going to use a discrete analog of Chebyshev nets. And then in this global formulation, we're going to see a reformulation of the smooth problem combined then with the discrete formulation. So are there any questions so far? Okay, then let's move on. So we'll start with the design space of singularity-free Chebyshev nets. This is joint work with a couple of groups in computer graphics, and Akash Garg, Bailan Deng, Younghao Yue, Eitan Grinspan group at Columbia, Mark Parlee's group at EPFL, and Max Wardetsky at University of Göttingen. So the idea, like I said, is you have some shape in mind, like this sculpture here. You want to take a single piece of wire mesh and make the best approximation that you can to this shape. Wire mesh, as we see, is actually modeled also by a Chebyshev net. So the guy who I did the elastic gridshells project with, what we did was he took a kitchen strainer and he cut it out, and it actually, the shape that then flattened in the domain fit exactly with Chebyshev's prediction for what that spherical cap should have. And so the main difference between what I'm calling a sort of wire mesh modeled by a Chebyshev net and the true Chebyshev net is that instead of having an angle, because we don't want to allow singularities, for a real piece of wire mesh, you have angle bound. So here, for example, all tangents are between 45 degrees and 135 degrees with respect to each other. So you cannot shear arbitrarily small or arbitrarily large. Computationally, right, we tried to take the approach of starting with some Cauchy data and evolving it using a hyperbolic approach. But as one can expect, sort of this local existence gets you only so far, right? I mean, you try to place down these initial data, you evolve from these initial data, and you see that you immediately sort of run into your angle bound where you don't expect it. So we couldn't overcome this by trying to sort of choose our initial data very well, because it was very sensitive to the choice of initial data. So we needed a whole new approach to throw this one out the window. So the key insight here was actually to turn to a discrete analog of Chebyshev nets. So don't try to model the PDE that governs the smooth Chebyshev net, but instead try to think of a discrete analog of Chebyshev nets from the get-go and use that explicitly in the model that we construct. And here we're going to turn to a field known as integrable discrete differential geometry. Okay, if you don't know what those words means, but let's focus a little bit right now on integrability, right? So integrability here, let me give you an example. So a Chebyshev net is governed by this hyperbolic nonlinear differential equation. And when k is equal to -1, which means we're studying actually pseudospherical surfaces like we see here, then the differential equation collapses to something called the Sine-Gordon equation. And this is studied in the context of mathematical physics, and is actually known to be a very special differential equation, because despite its nonlinearity, it has a certain explicit solution, linear superposition principle, lax pairs, and many different types of conserved quantities that are associated with it. And there has been much research in trying to take sort of discrete integrable systems and to understand if that discrete analog of the smooth partial differential equation can actually retain these integrable or these exceptional structures. And one example of this is if you look at the Sine-Gordon equation, you can write down a particular Sine-Gordon equation on a lattice, which exhibits these extra remarkable properties. And one of the algebraic techniques there is to actually generate a surface in 3 space from this finite difference equation. So what that means in practice is that you get a map from the lattice to 3 space, and what you get, the object you get in 3 space is a non-planar quad mesh, right? And this is explicitly generated without regards to some underlying geometry, just from this finite difference equation. But it should correspond, and it looks like a pseudospherical surface that's in Chebyshev parametrization. And the observation here is that it in fact is a quad mesh with all edge lengths equal. And so what you do is you use that to define a general class of discrete analog of Chebyshev nets as quad meshes where all edge lengths are equal to each other. One may have said, okay, you know, looking at the definition of a smooth Chebyshev net, you can guess that this is a nice analog, but here gives sort of a deeper understanding of why we should call these things discrete Chebyshev nets, because of the relationship to discrete analogs of underlying partial differential equations that retain an integrable structure. And just as in the smooth case, we retain this ability to shear up to a certain angle bound. So how does this definition actually help us in the design of these sculptures? Well, what we can do is we actually say, okay, instead of trying to start with some initial data and propagate along the surface, we search for a discrete Chebyshev net close by a given surface, but we allow for small deviations, right? So different from before, where we propagated exactly along the surface. Here, we just ask that the quad mesh be a discrete Chebyshev net, all its edge lengths should be the same, and B, it should be close to the surface that we have in mind. And just by doing this, we were able to get beautiful approximations of more complicated shapes, and the deviation to the surface were actually less than the wire mesh spacing of the underlying model. So here, for example, this is a mask that I built out of wire mesh, and its sort of approximate total discrete Gaussian, total Gaussian curvature is 66, which is far beyond the sort of known theoretical results of 2 pi. And so this gives us sort of some computational evidence that the class and the space of Chebyshev nets is much richer than sort of our current understanding from analytical results. So the summary of this aspect in this portion of the talk is that you can try to understand the material constraints by encoding them explicitly in a parameterization or in sort of some language of differential geometry. And then don't look at necessarily the underlying equations of that object, but really think about, okay, what is a discrete analog of this object that I'm studying? And maybe that will arise in some unexpected place. Like here, for example, by studying integrable differential geometry and its discrete analogs led us to a definition, or actually we harnessed the definition that was known for discrete Chebyshev nets. And this is, we found much more satisfactory than trying to overcome the challenge of this hyperbolic compatibility condition on the original surface. So for the remaining time, I'm going to talk about building Chebyshev nets and in real applications where you have more than one patch. You can probably see, it looks like we're almost at the end of the talk, but actually I will go much more in depth in this last section. So please stop me at any time if you have questions about it. This work is end of 2019, like I said, and is done in collaboration with Albert Churn, Miri Ben-Chen, and Amir Vaxman. And what it does is it sort of rephrases this Chebyshev net problem in terms of commuting polyvector fields. So let's talk about what each of these words mean and how they help in solving the Chebyshev net problem, which you see here. We have the sort of classic bunny, which is used in computer graphics research. Here is a that's right. So we have a quick question from Sven. Let me back up for a moment. The question is, was this mask molded, but actually found by the discrete Chebyshev net? Exactly. Okay. So sorry, so the question is, the mask is not molded, but found by calculation of discrete Chebyshev nets. That's correct. So the way the mask is made is I take the calculation from the discrete Chebyshev net. I then 3D printed a scaffold, which told me exactly where to map every single wire, basically, onto this 3D scaffold. And then I pinned the piece of wire mesh using the explicit parameterization that I have from the domain onto the scaffold. And I let it sit there for a couple of days, and the wire mesh is plastically deformed and into the shape. So here, actually, maybe you can see there are some small pinholes where I pinned it onto the scaffold. And that scaffold shape was predicted in advance from the discrete Chebyshev net. It is slightly deviated from the initial mesh that was put into the that was put as the sort of the target shape. Yeah, we were really, really excited with these results. And at the beginning, I think I showed also that we had this big torso where also we did that. Maybe even you can actually see here, you see there's some red and some green. That's from the coloring that we used to do the map, to actually record where we should pin each of those points. We drew the whole thing using different colored pens, and then I cleaned the mesh after we had made the shape to remove that coloring. Yeah, thanks for asking the question. Okay. Can you still hear me? Actually, it seems like maybe my headphones will die. I hope not. Okay. So sort of the first question that we want to tackle when we want to understand global Chebyshev nets on a target shape is, what kind of singularities do we want to allow, right? Because as we saw previously with the hemisphere, if you go down into the southern hemisphere from Chebyshev net's solution, what you get is actually a complete collapse to points. And this is not a singularity which can be physically manufactured. And so we have to reformulate the problem to get a different type of singularities. And those singularities are not these ones, right? Not where the angle collapses to 0 or pi, but rather branch singularities, right? So instead of having coordinate singularities, we want to study branch singularity solutions to the Chebyshev net problem. Here, if you go around this, this branch point, you can see that the Chebyshev net itself still satisfies an angle bound, which means it can be built from real fabric. So great, we've now decided that we want to use sort of these physically realizable branch singularities by piecing together multiple patches instead of using coordinate singularities. But we've now run into the same problem again, which is where do we put them? And how do we know that that's a good place to put them? So the idea here is to actually take this Chebyshev net problem and reformulate it using sort of differential coordinates as opposed to a parametrization. So the classic formulation is you have some sort of manifold, you want to find a parametrization from the UV plane onto the surface, which preserves the unit length condition of the tangent vectors along these two directions. Alternatively, we can go the other way around, right? We can say that we take two tangent vector fields along the surface that are both unit length and ask that they integrate into some parametrization R. So what does it mean to integrate into a parametrization? Well, it means that if I flow a little bit along the sort of the U tangent vector field and then V, that's the same as if I had gone the other way around, right? So two vector fields commute with each other. Going this way and then this way is the same as going the other way around. And this is encoded in the definition of the Lie bracket. So the differential coordinate formulation of a surface, of a Chebyshev net on a surface will be, we want to find two tangent vector fields, both of which are unit length, such that their Lie bracket is 0. And then we know that there exists a parametrization which we can integrate into a Chebyshev net, theoretically. So recall that this sort of classic formulation leads to a hyperbolic problem with coordinate singularities. And what I found really sort of very exciting is that this formulation on the right can actually be formulated as a variational problem. And the type of singularities that arise here are branch, and their location is explicitly given by solving the problem itself. So we don't have to specify them in advance. They're emerging from the solution. So how does this work? Well, in order to understand how it works, we first have to understand how to encode these branching. So what is the problem? The problem is if I have sort of U and V, these two vector fields along the surface, then if I move around a branch point, it might be that I've actually flipped my U direction or my V direction with respect to each other. And so to overcome this, instead of studying sort of pairs of tangent vector fields, in the computer graphics community in Diamante et al., they introduced this notion of a polyvector field, right? So a polyvector field says, use the whole cross field, sort of the whole field given by U and minus U and V and minus V. Precisely, this means that we have some action, sort of like a generalized rotation, where I start with U and V, and then I apply pi, and I get V minus U, apply pi again, minus U minus V, and all the way until I go 4 times, and I come back to the identity. And so this polyvector is given by a pair of tangent vector fields modulo the group generated by this action. But you can think of it just as you think of the whole X from the vectors, from the two pairs of vectors. And these objects are well defined across a branch cut because we don't notice the fact that U and V may have swapped places or gone into the negation. And we're actually looking now at a multiple covering of this surface. So what are the implications for finding a Chebyshev net? Well, let's go back and think about the Chebyshev net conditions. Well, actually, they're both also well defined for polyvector polyvectors. I can just say that I want to only study polyvector fields with unit length, and the Lie bracket is actually invariant to this group action. So therefore, asking it to be 0 is also well defined for polyvectors. So the reformulation of the problem is, given a surface, try to find a polyvector field, which is unit length and commutes. This you can actually write down by as a global minimization problem and split into two components. The first component here encodes the Lie bracket, and it can be thought of as something like an anisotropic Dirichlet energy, since it's built out of the components of the covariant derivatives. And then on the right, we have these two unit length constraints, which will encode with a 1/epsilon squared value. Now, in the world of optimization problems, this type of problem is actually well known. It's known as a Ginzburg-Landau formulation. And these Ginzburg-Landau formulations have a set of very remarkable properties. So for example, for a single vector field that we want to minimize, that we want to solve for over a surface, then actually minimizing the Dirichlet energy of that vector field subject to this sort of inextensibility, this sort of unit length constraint written in this way, automatically gives you locations which concentrate the energy, which correspond to singularities, and away from these sort of epsilon balls where the singularities have concentrated, you get the unit length being completely satisfied. And it's equivalent, as epsilon goes to 0, to minimizing the Dirichlet energy subject to the unit constraint everywhere away from this unknown singular set. But the really surprising and amazing thing about this formulation above is that actually you get the location of the singular set throughout the process. And so this problem that we have for global Chebyshev nets now has the same flavor, right? We want to have something like an anisotropic Dirichlet energy and some unit length constraints, which gives us a variational problem with emergent branch singularities. So does it actually work, right? I mean, you have to, it's nice to have this theoretical reformulation of the problem, but now we have to implement it to see whether we can use it both computationally and hopefully all the way to fabrication. So for example, here we take a human body and we do a global optimization for a polyvector field that is unit length and commuting. And what we see is that we get a concentration of singularities of this polyvector field exactly along the places where we see the seams arising in our garments, which I thought was really cool, right? I mean, it's like what you would expect. You have, if you want to build something out of woven fabric and it looks like a human body, then you should have concentrations of singularities along the places that we put seams. But how do you actually get the Chebyshev net itself from this polyvector field? Well, what you do is you optimize for your polyvector field. Then you integrate it into a quad mesh where each of these branch singularities maps to a point with non-valence 4 vertex in the quad mesh. And then what we can do is we can post-process the quad mesh as a discrete Chebyshev net. But here, we do not ask it to be close to the target surface. So we just ask for it to be a discrete Chebyshev net from the resulting quad mesh. And what we get is this sort of really surprising and cool result of global discrete Chebyshev nets that are actually physically manufacturable. So here, for example, is this bunny again. And Albert and I, we then took this multi-patch design and cut it out into the 5 pieces that we see on the board. 1, 2, 3, 4. Yeah, 5 pieces we see on the board. And then you can stitch it together to get the global solution. So here you see the singularities corresponding here and here, and you get singularities along the here. And what you can't see, but I'll show you in the next picture, is actually that away from the singularities, you get alignment of the 2 pieces across these branch cuts. So up here we see a singularity, but then here you can follow the 2 inextensible directions, and they flow smoothly across across this branch cut. So if we were able to manufacture it in a way that we only had singular points and no branch cuts, we wouldn't even see that the branch cuts are there, which is what was predicted by the Ginzburg-Landau formulation. We have a quick question here. Is there a visible difference between the quad mesh and the discrete Chebyshev net? Sometimes there was a visible difference, but it seemed to be quite minimal. We have in the article we have some quantifications of how much post-processing was required by the discrete Chebyshev net and how it sort of distorted the shape. So we can go back and see here. One thing that you see is that here on the surface, the vector field captures this sort of circular region here. And here we see a squarification in the discrete Chebyshev net. So each singularity kind of pops out as a cone point because there's nothing regularizing it to stay sort of more curved in the region next to it. Right, so actually even in our physical implementation, we were able to align neighboring patches so that they agreed away from the singularities. We hope now to sort of use this result to try to find new applications for Chebyshev nets. Like here we see a branch stent or an architectural grid shell that's built out of things that don't have valence 4 everywhere. So the idea is really, it might be that by harnessing differential geometry, both reformulating in the smooth case and then combining it with discrete theory could help you to overcome sort of a global optimization problem that may seem very daunting to begin with. So are there any questions about this sort of global Chebyshev nets before I zoom all the way back out and sort of give the conclusion to the talk? Okay, so what I just want to say here is that what I talk about today was actually sort of one example of a meso-structure that I like to think about, right? It's just what we saw is that we can study grids of inextensible rods. These could be something like an architectural grid shell or an elastic grid shell, where there's really elasticity driving the system, but actually it seems to be governed by the inextensibility constraint. It could be something which is plastic, like the wire mesh sculptures that we built. Or it could be something like our clothes, like the wire mesh, sort of like the fabric covering that we were able to make for this bunny globally. And the idea was to use tools from differential geometry, both reformulations in the smooth case and discrete analogs arising from integrable differential geometry, to come up with the models for these systems. So the hope is that we can actually use geometry and topology to understand many different types of meso-structures and discrete meso-structures and the properties and behaviors that underlie them. And sort of just as a small teaser in this direction, I want to say that, okay, I have a question here. Are there any existence and regularity results proved for the Ginzburg-Landau type energy minimizers? In the classical case for Ginzburg-Landau, yes, there are many existence and regularity results proved, but for our reformulation, we don't have any. We really were trying to focus on the sort of the computational aspect and fabrication aspect here. But this is, I think, is a very interesting question. It sort of has some subtleties, which let me sort of be very honest here, which I wrote down here at the beginning of the slide. Because of the anisotropy of this Dirichlet norm, you don't get a strictly elliptic problem. So you have to use a mild regularization in the polyvector formulation to smooth your polyvector field away from the singular points, which makes it a little bit more challenging in analysis than the straight, than the sort of the classical Ginzburg-Landau formulation problem. Yeah, so I just want to quickly say in my last 5 minutes here that this sort of overarching goal of using geometric principles to understand shape spaces, we took sort of a small step in this direction where we studied a sequence of objects from discrete integral differential geometry, and actually using the fact that there's often an equivalence between very special curved geometries in special coordinates and integrable PDEs for mathematical physics. There were many sort of results that were known in the smooth case, and then discrete integrable systems and the rise of difference equations has given rise to many different types of special quad meshes, like these one for discrete Chebyshev nets. And just recently, we were able to study all these different types of quad meshes and introduce sort of a general notion of curvature for an arbitrary quad mesh that encapsulates all of these very special cases. So in joint work with Tim Hoffman and Max Rardetsky, we sort of proved that there is a geometric theory for curvatures that assigns the correct curvatures to these discrete integrable quad meshes arising from very special finite difference equations. But the theory itself that we built really is just purely geometric, and the hope is that we can use this quad mesh theory and to help us better understand applications to a variety of different meso-structures more than just the discrete Chebyshev nets we saw in this talk. So that's it, and thank you very much for inviting me to speak today, and I would love to hear more questions if you have them.
So thank you very much. Are there questions, preferably on the microphone? So if Philip doesn't want to read this, I can read this. Can you also exclude branch singularities in certain regions of the surface?
At that moment, we haven't, we didn't look into that, but you know, it could probably be added as an extra constraint to the optimization. So one thing that we did do in the sort of the wire mesh project where we had a single patch, there we could highlight regions where we asked the discrete Chebyshev net to be closer in that region as opposed to in other regions. So you could really get like the important features of the face, for example, right? It'd say like pull away from, you know, make my neck a little thicker so that I can capture my nose better.
You have these global constraints. Can you still hear me?
Yes, we can.
Okay, because my headphones just died, so now I'm on my display audio.
Okay. Any other questions?
I have a question. Stephen Watson, sorry for coming in late to the call. I caught the tail end. I wanted to come to this stitching that you did at the end. You had this cutting and stitching, and you talked about the smoothness of the join.
Yes.
So my question is, the Gauss curvature is concentrated at the vertices. You talked about this square foot, for example, in the teddy bear example.
Yes, so not all the Gaussian curvature, just because we don't have a regularizer on the discrete Chebyshev net, right? So we don't ask the discrete Chebyshev net, for example, to not have points that look like this. We don't put a bending energy on on these terms. Yeah.
So in the teddy bear example, you had essentially a concentration of the Gauss curvature at points.
Not everywhere, just in the neighborhood of that point, right? So here, for example, this is non-zero Gauss curvature. It's not a developable approximation.
But my question was going to be, if I look at the mean curvature along the stitching, so you talked about that smooth join.
Yes.
Does the mean curvature jump across that join?
No, this is just this in the model. This should be just sort of a C infinity quad, right? So away, the Ginzburg-Landau hope is that away from your singularities, you actually get a perfectly smooth solution. And this is just showing that you can make it align in real fabric. That's all. Here, of course, it's not, right? It's not the same rod. So it's two things that are actually overlapped and stapled together. But if I was better at constructing, then one would theoretically be able to make it with only non-smoothness at the singular points.
Okay, thanks.
Yeah. That's what we see here, actually. Yeah. Yeah. Mm-hmm.
Sorry. Any other question? Then let's thank Andrew again.
Okay.